Hello there and welcome back to another video. In today's video, I'm going to be turning this old power supply into what I think is a really awesome, high power, dual channel benchtop power supply for use in powering all kinds of electronics projects. This is a power supply that I pulled out of my Dell R720 server when I upgraded its power supplies a while ago. This unit is capable of providing 12 volts DC at up to a little over 60 amps, which is a ton of power. However, with the projects that I end up doing most of the time, and the projects that I'd assume you're also probably doing most of the time, 60 amps of current at such a low voltage isn't incredibly useful. Thankfully, we can turn the output of this power supply from something kind of useful sometimes, but only for specific projects, into something very useful for all kinds of projects by using these 1500 watt boost converter modules. These things are super cheap, being about $25 a piece, and they should be able to take our 12 volt supply and boost it all the way up to 90 volts. Importantly as well, these converters are rated for a lot of power, although that 1500 watt rating that they tout doesn't really apply in our situation. These converters are good for 1500 watts or 30 amps, whichever comes first. In this case, 30 amps will come first because 12 volts at 30 amps will only be 360 watts. So we'll only have an output of maybe 300 watts per channel from this power supply, but this is still a really good amount of power, and we can have a very good voltage range at that amount of power. Anyway, I picked up 2 of these modules to use as the core of this power supply in conjunction with the repurposed server power supply, which I had now figured out how to signal to turn on while not inside a server based on some information I found on this forum post. Link in the description. Now, with my initial plans for this project being to have this power supply be fully digitally controlled, I started out this project by partially taking apart one of the boost converters and tracing its feedback circuit with the hope of being able to use digital potentiometers to control its output voltage as opposed to the regular old trimmer pot. Sadly though, the high voltage range of this converter means that I couldn't find any digital potentiometers that would work in place of the mechanical one due to limitations in the voltages that they can handle. The feedback system on this module works in a way so that the output voltage flows directly through the trimmer potentiometer, and the voltage drop across that potentiometer can be quite massive, way higher than any of the voltage ratings that the digital pots I could found would support. So I sadly had to call it quits with that part of my plan pretty early on in this project, and instead I had to replace the digital potentiometers with some mechanical ones. Thankfully, I was able to find some 10-turn potentiometers in both 5 kilo ohm and 100 kilo ohm resistances for the current and voltage adjustments, respectively. And after I had a pretty decent idea of the main components that I'd be using in this power supply, I took a bit of time to figure out roughly how I would lay them out inside of the box. And after I had a solid plan, I went ahead and began the circuit design for the main motherboard in this power supply that would control things such as the voltage readouts and the other power supply's functions, such as toggleable outputs. The control board will be based around a Teensy 4.0 microcontroller, and its main purpose is to measure the voltage and current output of each of the 2 boost converters. It also handles some other tasks, such as turning on the server power supply when the power supply's main switch is turned on, and it also has some inputs for switches and outputs for relays that will be used to toggle the output terminals on and off, a feature that is missing on the bench power supplies that I own and that I really wish they had. Beyond that, there are some other small circuits on the board that handle things like protecting the microcontroller's ADCs while the power supply boots up from possible voltage spikes, as well as supplying a 5 volt supply to the LCDs and the microcontroller. Overall, the board is really light on components and functionality, so you might be wondering why it's so darn big. Well, the reason that I designed these boards to be as large as they are is because I wanted them to be a structural element of the power supply. I wanted the boost converters to mount directly to them and have their connections to the PCB very close and very simple. I also liked the idea of the PCB forming what's basically the full power supply module without having other parts for other functions strewn about throughout the chassis. After I had my schematic and PCB designs finalized, I went over to the website of the sponsor of today's video, PCBWay, and I placed an order for my PCBs. PCBWay is a company that offers high-quality custom manufacturing services at very reasonable prices. They offer a myriad of different services, but some of my favorites are their 3D printing service, sheet metal production service, and of course, their PCB manufacturing. I've always had great experiences with their services and highly recommend that you check them out at the link in the description if you like to build things and think that one of their offerings might be of use to you in your next project. Anyway, a while later, the PCBs arrived and the quality was just as good as always. It also seems that they sent me a 6th board free of charge, possibly due to their panelizing process allowing for it. I ordered my boards with a white solder mask, and I also ensured that when I was ordering them, I ordered them as 2 ounce per foot squared boards. This means that the copper layers on these boards are much heavier than the copper layers on more standard 1 ounce per foot square boards, which is important because there are some thick traces on these boards that need to be able to carry a very large amount of current. But anyway, I got straight to work soldering all of the SMD components onto one of the boards. I tried to keep this board decently light on SMD components, but there are still quite a few 0805 size resistors and capacitors. Thankfully, they're not that hard to solder, even by hand and without magnification. The trickier parts to solder on this PCB are the 2 ACS 71240 Hall effect current sensor ICs, which are in the SOIC 8 package. These chips aren't too bad on their own, but several of their pins are connected to very large copper areas on the PCB because all of the current of the power supply's outputs goes through these chips, and this can make it a bit painful to get enough heat into the joint for a good solder connection. But after a while, all of the SMD components were soldered on, and I could move on to all of the through-hole components like the transistors, diodes, and resistors. The transistors and diodes can be soldered on like normal, however the through-hole resistors need to be measured with a multimeter before being installed, and it's important to keep track of where you put each measured resistor on the board. There will be spots in the code for these values later, and since these resistors form the voltage dividers that measure the output voltage and the sensor voltage from the current sensors, having their exact values will increase accuracy significantly. After all of those parts were installed, I soldered the pin headers, screw terminals, and the microcontroller to the board. I also made sure to install the 2 relays that protect the microcontroller's ADC pins from any possible voltage spikes when the boost converters start up. After the board was all built up, I attached the 2 boost converters to it using some M3 bolts and the standoffs that were included with the converter modules. Then, I made some jumper cables out of 12 gauge solid core copper wire to connect from the positive output terminals of the boost converters to the screw terminals on the motherboard. After those connections were made, I powered the board up with a 12 volt supply from my bench power supply to test for functionality. When this is installed in the final power supply build, this PCB will get its power off of the power supply's 12 volt standby rail, which is capable of providing 3 amps and is on whenever the power supply is plugged into wall power. I then plugged the PS kill and PS on wires from the server power supply into this PCB, and with a super simple test code, I ensured that the trigger to power up the server power supply worked as expected, which it did. Then I took the server power supply and the main power supply PCB and laid them out on my work mat to get a general feel for how large of a case I would be making, and how I should cut the ABS sheets that I was planning to construct this enclosure out of. I had originally wanted to 3D print the enclosure for this power supply because it would be easy, but the internal parts ended up being too big to fit in a monolithic enclosure that my Ender 3 3D printers could print, and splitting a 3D printed enclosure into multiple parts is always a disaster for structural integrity when your tolerances are crap. So, in the end, I settled on an aluminum subframe and some ABS sheets on the top, bottom, and sides, with 3D printed front and rear panels so that I could easily make the intricate cutouts for the pots, screens, terminals, and switches. After I had a rough idea of the enclosure I would be making, I took a quick break and desoldered all of the trimmer pots from the modules for current and voltage adjustments, and instead soldered some simple DuPont wires onto their pads, as I realized I forgot to do this earlier. After that, I was back on track with planning the enclosure and figured out a layout for the front panel switches, screens, potentiometers, and banana terminals. I then built up a frame out of some 2020 aluminum extrusion, and then I started cutting and drilling some 1/4 inch thick ABS sheets that will make up the top, bottom, and sides of the enclosure. I drilled holes in the sheets for M5 screws that would allow them to mount to the 2020 aluminum extrusion using some T-nuts, and it all went together flawlessly. I then took some lengths of basic aluminum C-channel and marked drill points in them so that I could mount the 2 halves of the 3D printed front panel to it and have a single, strong front panel. I was able to get the panels mounted to the C-channel pretty easily, although the final construction didn't come out quite as square as I had wanted it to, probably due to my lack of a drill press and some errors in my markings. In any case, I was still able to get this mounted to the front of the chassis with some more M5 bolts and T-nuts, and so I'm not going to complain too much about how it turned out. But instead of mounting this part to the chassis immediately, I attached several of the front panel components to the front panel so that I wouldn't have to do this while inside the cramped enclosure. I messed up the spacing for the mounting holes on the LCDs, and so I ended up just hot gluing those into place instead of using their originally planned M3 bolts and nuts, but the rest of the holes were just the right sizes and in the right places. I stayed away from mounting the potentiometers just yet, but did take this time to solder some long extension wires onto their terminals that will come in handy later. I also soldered male headers to the ends of these extension wires so that they could easily plug into the DuPont connectors that are soldered to the boost converters. I then did the same with two small toggle switches, except I put female headers on the ends of these extension wires so that they could easily plug into the PCB. The next part in this project for me was getting the server power supply's connections to the inputs of the boost converters started. These connections need to be able to handle a ton of current, up to 30 amps, and ideally, they're capable of handling up to 40 amps, as that's what the fuses on the boost converter PCBs are rated for. I wouldn't want the wires to melt before the fuses, so I'm building this with lots of headroom in terms of current delivery capacity. On the input sides of each of the boost converters, there are 2 terminals for a positive connection and 2 terminals for a negative connection. This is really convenient because it means I can run 2 12-gauge wires to the positive and 2 to the negative, for a total rated 40 amps of current capacity. Now, working with this thickness of solid core wire inside of a cramped enclosure is, pardon my language, but complete f***ing hell. I was not going to have the patience to run monolithic wires from the terminals of the converters to the terminals of the power supply, and to try and solder them in place to the power supply with my underpowered soldering iron inside the cramped enclosure while the wires were probably pulling against me. So instead, I cut 8 roughly 2-inch lengths of the wire and stripped them and bent them all the same way, taking roughly 6 to 7 millimeters of insulation off of one end and 11 millimeters off of the other end. The end with the smaller length of exposed wire then got soldered to the terminals of the power supply, 4 to the positive and 4 to the negative. Then, the ends with the 11 millimeters of bare wire all faced in the same direction, where they'd be able to quick connect to the wires that attach to the boost converter modules when I put the boost converters into the chassis. At the same time, I also made sure to solder some basic stranded wires to the 12-volt standby connection and to the main ground connection, and these will be used to power the main PCB. However, they'll first run through the main power switch to the power supply to control when we turn the system on and off. I then laid out the main PCB and the server power supply inside of the case to get a feel for exactly where I would need to drill the holes for the PCB and PSU mounting brackets. The PCB mounts to the bottom of the case through the use of 6 M5 screws that connected to 6 100mm tall M5 standoffs, which finally secure the board with some nuts. This was just to get a feel for how things could fit inside the case, as at this time my second power supply bracket was still printing, so before I came back to mounting and wiring up the main power electronics, I pivoted back to the front panel for a bit. I mounted the 3 toggle switches in this design to the front panel, with one switch that has no wires soldered to it on the panel's far left, and the 2 that have wires on them to the right of that switch. I then screwed my binding posts into the panel and started to work on a really important thing for a power supply to have that isn't included on my PCB: reverse voltage protection. If you use a power supply to charge a battery, or anything similar to that, there's a risk that if you accidentally flip the polarity when making the connection, you can backfeed a damaging voltage into your power supply. There are several ways to protect against this, but the cheapest and simplest way to do so is to use a big diode in reverse across the output terminals. This diode will do practically nothing while the power supply is running normally, but when a reverse voltage is connected to the power supply's output, it should work as a crowbar circuit and short out the connected reverse voltage, likely sacrificing the diode in the process, but protecting the power electronics behind it. I chose to use some of these really chunky 6-amp diodes that came out of an audio amplifier's bridge rectifier because I wanted the reverse voltage protection to have a higher chance of surviving a reverse voltage than if I had used a smaller, weaker diode. However, something like a regular old 1N5408 will work just fine. Anyway, I soldered some small ring terminals onto the 2 diodes and then placed them on the binding posts to complete the reverse voltage protection. And I took extra care when doing this to make sure that I placed the diode in an orientation where no current will flow through it normally, so that I didn't short the power supply's output with the diode. By this time, I had my 2 server power supply mounting brackets done, so I could mark the drill locations for the brackets in the case. It didn't matter where the one that's closer to the power supply's terminals is located, but I kept in mind that the bracket closer to the back of the unit holds the power supply in place from being pushed into the box by catching this little step where the power supply's fan is. Therefore, I made sure to position it in a way that it wouldn't allow the power supply to slip into the chassis when it's mounted. I also made sure to use a drill to create some small slots for the power supply's locking lever tabs to lock into. This will keep the unit from getting pulled out when unplugging the power cord, and also make sure that the locking tab isn't pushed against the bottom of the case constantly, which causes it to block the AC input on the power supply. After mounting the server power supply, I marked mounting spots for the M5 standoffs that hold the main PCB into place and drilled them out so that I could mount the main board assembly. I didn't fully mount the main board yet though, and instead just set it on top of the standoffs for when I'll later mount it in place after making all of the screw terminal connections to the boost converters. And now we're finally back to wiring time. Arguably one of the worst times when it involves using 12 gauge solid core wire in a small, cramped enclosure, and when you have no one to blame but yourself for choosing this wire. Anyway, the plan is to make wires that come from the boost converter's input terminals and line up with the pigtail wires that I soldered to the power supply previously. Then I'll use these really awesome inline Wago connectors to make all of the connections quickly and easily. These connectors are rated for 20 amps each and should do the job perfectly. And so I got to work making the wires that will go into the inputs of the boost converters, and I put some fork terminals on the ends of them so that they would fit nicely into the screw terminals and there wouldn't be any kind of shoddy connection. After painstakingly making 8 unique wires that were the right sizes and bends for their exact runs, I mounted them all to the boost converters on the bottom of the PCB, along with 2 long wires coming from the negative output terminals of both of the boost converters that will then connect to the negative binding posts later. After all of the screw terminal connections were finalized, I mounted the board and the chassis for real this time and made all of the Wago quick connects. Even though with the Wagos, wiring this thing up was anything but painless, I still think that these made this a much easier process than trying to solder inside the enclosure, and I'm glad I did it. I then made the connections for the power supply kill and power supply on wires so that the main PCB could signal to the power supply to turn on, and marked and drilled 2 holes to mount 2 car relays. These relays can handle up to 30 amps, which I figured would make them perfect for switching the main output terminals on and off, as we will have quite a lot of current coming out of this power supply. After mounting the relays, I soldered wires to them that plugged into the main PCB for controlling their coils, and then I soldered a 12 gauge wire from the PCB mounted screw terminal that was right above each relay to one of its switched contacts. The other switched contact will connect to the positive binding post of each channel with another small 12 gauge jumper once the front panel is on. Now I'm getting close to being able to mount and assemble the full front panel, however I still have one more thing to figure out, and that is the potentiometer wiring. It's important to connect the potentiometer pins to the correct pins on the boost converter PCBs, or things won't behave properly, or the knob will raise the voltage when turned counterclockwise instead of clockwise, which wouldn't be ideal. If you happen to be doing a project on your own that's similar to this in that it requires you replacing pots on a boost converter, here are some little tips to help you out. First off, make sure that the wiper pin of the panel mount potentiometer connects to where the wiper pin of the trimmer pot was. And if the knob adjusts in the opposite direction than you want it to, take the 2 connections that aren't the wiper and switch them. Also, don't change any connections with the boost converters powered up, as you could cause damage by messing up the feedback loop. Now it was time to mount the front panel, which was really awkward to do with all of the solid core wiring, and so I have pretty much no good footage of this because I had to get all up in the camera's shot to be able to see what I was doing. However, in hindsight, I might have been able to avoid this if I had remembered that I could actually unscrew and remove the 2 side panels of the chassis to access the back of the front panel better. Now the only wiring left to do was for the 12-volt standby rail, which supplies power to the motherboard. The ground connection just connects straight to the negative terminal on the main board, and the 12-volt standby rail connects to the board, but it goes through the main power switch first. After the front panel was mounted, I took the 4 potentiometers and routed their wires to the back of the chassis and plugged them into their DuPont connectors properly, and then mounted them to the front panel with the included nuts. I then wrote my basic code to power on the power supply and provide the voltage measurement and current measurement outputs, as well as to control the channel on-off relays. I would still need to refine it to get the voltage readouts as accurate as possible, which I would end up doing later by using a curve that I figured out with a quadratic regression based on several different voltage measurement points, and I also still had to calibrate the current readouts too. However, I was able to test the power supply for basic functionality at this point, and everything worked awesomely. That is, except for the voltage and current readouts, which were fully broken. But I was able to fix that really quickly because those issues were only caused by some simple errors. After I fixed the voltage readouts to be accurate within 0.1 volts throughout their entire range, and while also getting the current readouts functional but not yet calibrated, I began to run some load tests on the power supply, and that's when everything went quite wrong. I connected a load to the power supply that at 40 volts drew 4 amps of current, and when going to turn it off, I heard a buzzing and crackling sound and noticed that the load was still drawing current. I then saw a bit of smoke come out of the power supply and quickly shut the whole thing down. Sadly, none of this was on camera because I had the unit at my other desk for debugging the program. However, I do have this thermal camera video which shows that the relay was very hot after this event. And that's when I realized a pretty sizable mistake that I had made. These were car relays. They're really not designed to break more than 12 volts DC, maybe 24 at max. The 40 volt arced across the contacts, heated up the relay, and burnt it fully out. Sure enough, after doing an autopsy on the relay in question, I could see that the contacts were fully welded together and that the plastic case had melted a bit and one of the contacts had even moved. This was really disheartening because I was so close to having this project finished, and for reference, as I'm writing this script, this project is passing its 3 months in the works mark. And as I'm doing this voiceover, it's getting close to 5. In fact, some of the really observant among you might have noticed that the footage from the earlier parts of the video is so old that it predates me wearing the ring that I always wear now. All of that goes to say that I really wanted to finish this project at this point, and so out of what was basically a panic, please just let me finish this project, I'm so close, I purchased 2 solid-state relays. However, what I failed to remember was that solid-state relays are hardly comparable to relays at all, as they do have a very noticeable voltage drop across their contacts, at least the ones that I have do, and that's because they're BJT based. This would make them unacceptable for the output of my power supply because the voltage drop isn't even something that I can just offset in the readout as it changes with current draw. I could come up with a current to voltage drop curve that I could implement in the code to keep the voltage readout accurate to the output, but that still doesn't negate the issue that the voltage on the output of the power supply will drop noticeably as current draw increases, which is kind of a big no-no for a bench power supply. I also couldn't redirect the feedback circuit of the converter to be post solid state relay, as although it would fix the voltage drop issue, I wouldn't be able to turn the relay off without sending the boost converter into a panic, making it think that its output is 0 volts. It's likely it would just go full send in that case and end up blowing everything up. So yeah. Although the solid-state relays do their job fine for what they're meant to do, they're not suitable for the task at hand. And so it was off to the internet to see if I could find any suitable relays. I did manage to find some, which are these Omron G2RL-1A-E-CF-DC12 relays, quite the mouthful. They're only good for switching up to 16 amps, and so they will limit the output of the power supply somewhat, but after scouring their datasheet, I figured that they should have been suitable for switching the full 90 volt output at about 3 amps of current flow. However, to cut a long story short, as this video is already so incredibly long, they weren't. I was on and off about what I could safely call switchable with these relays, and after a lot of testing and revising, what I settled on was a 45 volt 10 amp rating, which is even more current than the power supply can output at that voltage. I threw this on the power supply as a label, which ended up getting changed a couple of times as I experimented more, so ignore the labels if they don't line up with what I just said. What I just said was the final call that happened later. Above 45 volts, it seems like this relay is only trustworthy to switch up to 1 amp safely, which is fine, but honestly, I'm kind of disappointed in these relays and in Omron. As far as I could tell from the datasheet, and I did a lot of research on these before buying them, they really should have been able to switch 90 volts at 3 amps without arcing. Maybe I'm misunderstanding something, and if I am, please educate me in the comments, but I was expecting these relays to be way more capable at switching DC than they actually are. I mean, seriously, the max rated switching voltage is 300 volts DC, and max switching current is 16 amps. Yes, the rated load is 16 amps at only 24 volts DC, but from what I found online, as long as you lower the current, you can raise the voltage and be just fine as long as the wattage is the same or lower. Moving on though, I installed these relays, which was a bit janky because they're PCB mount relays and they're not in a PCB, but I made it work in the end. I then went on to finish my labeling, mounting of the knobs, and then I started work on the back panel and closing the enclosure. The back panel of this power supply, like the front panel, is just 2 pieces of 3D printed plastic that are joined together with some shorter lengths of the same aluminum C-channel that was used for making the front panel of the power supply nice and rigid. The back panel also holds a small 80mm fan whose purpose is just to provide some general airflow throughout the chassis. The boost converter modules and the server PSU are the parts that will get the hottest, and they all have their own fans in them to keep themselves cool. However, with the boost converters in particular, if the enclosure was sealed, the air inside would slowly heat up and eventually their cooling systems would become ineffective. So having general airflow is important. This fan will be mounted to the back panel and will exhaust out of the back panel, but of course I had to drill some intake holes if it's going to be able to do that. So I took off the two side panels and with the help of a 3D printed guide, marked the spots for arrays of vent holes on each of the two panels. I drilled out these holes, and now the fan will be able to pull air through the front of the chassis and exhaust it all out of the back, keeping everything nice and cool. In practically the exact same way as the front panel, I was able to assemble the full back panel part with the fan attached and the two 3D printed parts bolted together through the aluminum C-channel, and finally the whole assembly was complete. And I can officially say that with that, this project is finally done. Man, this build took a lot of work and a really long time, considering that I started this project back in March. In any case though, let's take a look at how awesome of a power supply this is now that it's fully assembled. It's got two channels, each of which have separate voltage and current limit controls, as well as separate readouts on separate displays. In general, the voltage readouts are accurate to within 0.1 volts, although sadly due to the way that I designed the voltage measurement circuitry in this supply, these readouts do become minorly less accurate as the output current on a channel increases. The current displays have the ability to be super accurate, I just haven't gotten around to calibrating them yet like I did the voltage displays. I'll likely add a feature that measures and sets the offset voltage for the ACS 71240 sensors at boot up, so that the displays don't ever show a small current draw even when there's no current flowing like they do right now. Then, of course, I plan to apply regression to tune the measurement's accuracy across its range. Moving on, each channel of the power supply is capable of providing 12 volts at up to 16 amps, all the way up to 90 volts at a max of 3 amps. What's important is that the max output power at any voltage is below about 300 watts. Each channel can be independently switched on and off, however the switches shouldn't be actuated when the voltage is above 45 volts. Otherwise, if there's a high enough current draw on the output, the relays are likely to arc and destroy themselves. I haven't done any super serious measurements yet to see just how clean and stable the output voltage of the supply is. However, I do have a feeling this might be one of this supply's biggest downfalls due to how cheap the boost converters are. However, with a super limited test setup, I wasn't able to find any immediately glaring issues with the output ripple, so it might actually be decently okay. The other major issue with this supply is that the boost converters used are not of the isolated type. This means that the two channels cannot be wired in series to create a 180 volt supply or a dual rail supply that gives a positive and negative rail. The ground of channel 2 is electrically connected to the ground of channel 1, and so connecting channel 1's positive to channel 2's negative to link these in series would actually just short out channel 1. So if you had been wondering why I didn't build this supply with a switch to wire the output in series or parallel, that's why. No parallel connection is for a bit of a different reason than the reason that the series wouldn't work, but just know it still wouldn't be a good idea and could possibly cause a catastrophic failure. I ran some load tests on this supply and was able to easily draw 2 amps at 90 volts, about 10 amps at 30 volts, and 5 amps at 50 volts, which I'm pretty happy with. I wasn't able to properly load test the full range of output voltages and currents that this should theoretically be able to provide, because my load consists of some basic power resistors and is therefore quite limited in configurations. And so, it seems that it actually might be time to start a project where I build a high power constant current load. Seems like I could get some decent use out of it. Well, that's all that I have for you in today's video. I hope that you were able to at least enjoy it and maybe even learn a thing or two. In any case, I hope to see you next time. Goodbye.